Right, good evening, everyone, and welcome to this month webinar conducted by Institute of Physics Sri Lanka. I am Shanta Gamage, the president of Institute of Physics Sri Lanka. Before introducing our resource person today, I would like to warmly welcome all the participants of this webinar. Thank you for making the time to watch our seminar today also. So, as you are aware, the main objective of the IPSL is to promote and advance the science of physics in Sri Lanka. Therefore, we organize various activities related to physics. So, today our resource person is Dr. Jayakody, senior lecturer from the Department of Science for Technology of the University of Sri Jayawardhanapura. Thank you, Dr. Gaya, for accepting our invitation for our monthly webinar to talk about beauty of mathematics. So, in order to introduce today's resource person, I would like to invite Dr. Chathuri Nupiarachi, convener of the monthly webinar of this IPSL, and thank you very much. Over to Dr. Chathuri.
Well, thank you so much, sir. And it's my pleasure to welcome our resource person today. I will give a brief biography of our resource person. Hold on for a while. Yes, I'm getting her biography. So our resource person today is Dr. Gaya Jayakody. She is a mathematics enthusiast, and he is a mathematics educationalist also. She received her bachelor's degree in science, BSc, in physics back in 2002 with a first class from the University of Sri Jayawardhanapura. And her MSc is in mathematics education back in 2010 from University of Colombo. And her PhD in mathematics education back in 2015, she obtained it from Simon Fraser University, Canada, under the supervision of Professor Rena Zakix. And while in Canada, she was the recipient of the President's PhD Scholarship in 2013 and the recipient of the Graduate Student Research Award in 2014. Upon her return to Sri Lanka in 2016, she has actively worked as an advocate for conceptual and meaningful teaching and learning of mathematics. She joined the Faculty of Technology of University of Sri Jayawardhanapura in 2018, where she is currently working as a senior lecturer in mathematics. Her passion to uplift mathematics education in Sri Lanka is reflected in her frequently held media interviews and also her role in the ambassador for Sri Lanka in Global Maths Project. In addition, she is involved in a number of national level projects such as curriculum development of degree program in National Institute of Education, conducting mathematics, teacher training programs with Ministry of Education, and serving as a member of the setting panel of a number of advanced level papers with the Department of Examinations. She currently serves as the chair of Committee for Popularization of Science of SLAS Sri Lanka, and she is also the initiator and the co-founder of MetaHub, Mathematics Education Teacher Awareness Hub, the first ever web-based platform for mathematics teachers in Sri Lanka, which was launched back in 2022 November. So without taking much time, this digital platform is yours, Dr. Gaya. Over to you, ma'am.
Thank you, Dr. Chathuri, for that kind introduction. And thank you, Shanta sir, for having me for your webinar series organized by the IPSL. I'm delighted to be here. Hello, everyone. A very good evening to you. I'm not very sure. We have 12 participants. I'm not sure of the composition of our audience. I hope this must be mostly undergraduate students. So I will do my talk thinking that most of you are undergraduate students. So let me share my screen. I hope you can see it. So first of all, I know that this title that I have chosen for my talk sounds very cliche. Beauty of mathematics is something that you always hear. And I know what might come to your mind when you hear the phrase beauty of mathematics are, these pieces of math that are popularly known to be beautiful. Things like maybe the Fibonacci sequence, the golden ratio, fractals, beautiful pieces of geometry or number patterns and things like that. But today is a little different from what you typically see as beautiful in mathematics. Now, you may have heard people saying that mathematics is inherently beautiful. What that means is that math is in and of itself, intrinsically by itself is beautiful. But then you have to think about it. It begs the question then why so many people, especially learners of math, don't find math intriguing or fascinating? Why do a lot of people either find mathematics as a boring subject, a dry subject, or a dull subject? Why do people fail to see this beauty? So what I have to say is that math can be beautiful, but if you are seeing this beauty depends on you as well. So seeing this beauty of math, it lies in the way you interact with it. It depends on the way you engage with it. And it depends on the way you see it, you perceive what mathematics is. And also it depends on the way you understand it. So if you don't engage with it, and if you don't perceive it and make sense of it in a certain way, you are not going to this beauty of math that everyone talks about. So what I'm hoping to share with you are 4 aspects of mathematics, 4, let us say, features or attributes of math that makes it intrinsically beautiful. And also how, if you become aware of these aspects, if you become mindful of them, if you become educated of them, how you will start seeing the beauty of not just the ones that I mentioned earlier, the pieces of math that are popularly known to be beautiful, but also in every little piece of math, how you can see the beauty. So let us go ahead with it, right? And hopefully when I share these 4 aspects, you will start interacting with math a little differently. You will see math as a different subject, and you make sense of it in a different way, different to the way you have been trying to learn it or understand it. Right. So here's the first aspect of math that we might not think a lot about. Mathematics is a human creation. Where have we gone wrong? We might not see this. We might not acknowledge its humanness, and that affects the way we see math. Now, all different topics in mathematics that you've learned, concepts, procedures, ways of solving problems, everything that you've learned, and take a moment to appreciate and think about the fact that, is it a product of the human mind? If you think about it, that itself adds a lot of wonder to math, and it's something that you should let sink in, because it's something that we don't deeply think about, but because if you do, that adds a lot of fascination about mathematics. So let us go back and think about, I want you to reflect on, go back and think about different mathematical concepts that you have come across in your life, and think all man-made, mind-made. Start with numbers, starting from counting numbers all the way through to complex numbers are created by us. Algebra, algebraic expressions, equations, They are mind-made objects. They don't exist out there in the world. Functions, matrices, vector spaces. Think about objects. Points don't exist concretely out there in the world. Now, I want you to really think about this. This is one way in which mathematics stands out from a lot of other subjects. Take as an example, physics or chemistry or any other subject for that matter, and think about what the objects of study in those other subjects, what these other subjects study about. Think about physics. I think most of you are physics students or maybe technology students. What you study in these other subjects, the objects of study, they exist out there in the world. You go and study about them. They exist without you thinking about them. Now think of all these objects that you come across in mathematics, these structures, these mathematical objects. They don't exist in the world without you thinking about them. They're all mind-made. And that is why we say that math is abstract, if you have heard of that term. That's why we say it is abstract. It's all in the mind. But we do have ways of starting with a concrete level and moving on to that abstract level when you learn mathematics. But the fact that it's created by the human mind has to fascinate you. And the other thing is, what happens when we learn math is you usually learn mathematical concepts or procedures as the final product. What you learn is the final product. And when that happens, you learn through definitions of these concepts. When that happens, you don't get to see the thinking process that went into the creation of those mathematical objects. You don't see the efforts, you don't see the messiness that went into creating that. You don't see the thinking pattern, how people conjectured about things, how they failed, how many times they failed, and how much they had to observe, look into these structures, these patterns to come up with these concepts and procedures. So you miss to see all that, and you miss to see a little bit of beauty of mathematics when you don't think about it. So a common example that I take is numbers itself. Think about the creation of numbers, how complex numbers were created. Just trying to think about that has to fascinate you, how the human mind has created all this. Another thing that comes to my mind is you might be taken as an example, the binomial theorem. You can learn the binomial theorem just by its definition. But if you miss to see the observation process, the identification process of the structures and the patterns that went into the establishment of binomial theorem, you're missing out something. So this is something to keep in mind when you learn math. When you come across mathematics in the future, try to think about it. This was created by a mathematician. It was created by people. So that would add some beauty, and it should change the way you think about mathematics. Here's the second aspect of math that I think that we are missing on. Mathematics is conceptual. What do you mean by that? But where have we gone wrong? We perceive it as a procedural thing. I will explain what I mean by this. And this could be the main reason why a lot of people find mathematics boring, because they haven't seen mathematics in a conceptual level. So I will explain this in two aspects. One of the things that comes out from math being conceptual is that often there is a number of different ways and angles that you can look at a concept. Think about a concept, think about a problem. There is always more than one way. And you might be applying a rule to solve a problem, to do a math task, but you might not be having an understanding of why the rule works. If this is the case, that means what you have, the kind of understanding that you have about math is procedural. So you don't see the concepts underlying what you're doing. So you are not seeing part of its beauty. I will take an example. So I have picked a couple of examples based on very simple mathematics. The reason why I've taken very simple mathematics, like grade 6 math, is because I want you to see that even in the simplest math like that, not see to now, things that you have not thought about up to now. That has to do with the conceptual nature of mathematics. So let me give you a little task. Now look at this. I want you to be mindful of what comes straight to your mind when you see this. If I ask you to work out 18 times 5, what comes into your mind? Think about the thinking process that goes in your mind. If you were to do it, what would you do? I want you to think about it. If you can communicate it to me, that's even better. So when you think about now, this could have been any two numbers. I've chosen 18 and 5. Now, when you think about this little task, there are two things that play a role. One is how you perceive these two numbers. Would it not matter whether these two numbers were different? If whatever the two numbers I give you, would you jump to the same, maybe an algorithm to do this? So one thing that matters is how you perceive these two numbers. We call it number sense, whether you have a feel about the number 18 and 5, or whether they are just any whatever numbers that I may give you, whether they feel the same to you. That's one thing. And the second thing that will play a role when you're thinking about this is how you think about multiplication, how you have conceptualized multiplication. That's all. So if I if I take you to, I'm sure, okay, so if you can talk to me, it would be great for me to know how you thought of doing this. I think my guess is you may have, let me share a different screen. Let me know whether you see the screen. If what you did for 18 times 5, if what came to your mind and what you thought about is only the traditional multiplication algorithm where you write 18 and 5 one below the other, and you go 8 times 5, 40, and you put a 4 here and then 9. If that is how you did it, it's fine. But I want you to think about, can you do it can you think of a different way of doing this? Would anything else come to your mind, or are you stuck in this? So take a moment to think. What I'm trying to show you here is the nature of math being conceptual. If you have made sense of these things conceptually, you are able to flexibly think about this. Here's another possible way of doing this. I don't know whether you have, whether you know this. You can think of multiplication of two numbers as finding the area of a rectangle with the side lengths being these two numbers. So 18 times 5 is the same as finding the area of a rectangle of whose width is 5 and length is 18. And then you can very easily But once you have seen this concept, once you know how to conceptualize multiplication this way, it can happen in your head in a few seconds. So 5 times 8, this part of the area is 50, and this is 40, and the total area therefore is 90. If you write this algebraically, what I actually did was this. It's 5. I broke down 18 as 10 plus 8, right? But this is a different conceptualization of multiplication. It's a different way of thinking about multiplication. And here's another way. If you have this sense for these two numbers, 18 and 5, when you have to multiply by 5, what you can easily do is, now you have to do 18 times 5. You can halve this number and double this number, because double of 5 is 10, and multiplying by 10 is a piece of cake. If you halve 18, it's 9. And then if you double 5 is 10, the answer is 90. So this is a handy strategy that you can use whenever you're multiplying a number by 5. So it's just that I have offered you 2 other ways of looking at the same little activity of multiplying 18 by 5. There are more ways of doing it. And that ability to look at tackling, to tackle the same problem comes from the conceptual understanding of math. So let me go back to my screen. I think I have 2 more. Here's another one. 1 divided by 2/3. Again, I want you to think about how you think about this. How, if you were to do it now, how would you do it? Do you always follow, because you've learned an algorithm? This is why I said you think about mathematics procedurally, then you would jump to a procedure. If you have not seen this conceptually, you would not be able to do this little activity without using the rule. Now, I know that you know how to follow the rule and do this. What you would do is turn the division into multiplication and turn the fraction upside down, and you can get the answer. I know you can get the answer, but do you know what happens there? If you didn't have the rule, would you be able to do it still? Or would you at least be able to explain why that rule works? Again, I don't know whether you can talk to me if you can do that. I feel like, so, okay, let me go back to this. Do you see the screen? Yeah. Again, 1 divided by 2/3. Now, the traditional way of doing this is by just blindly. I'm saying blindly because I know you're doing it blindly. You can blindly follow the rule. 1 times 3/2. You change it upside down, and the answer is 3/2. That is 1.5. Now, someone who has a conceptual understanding of this, of numbers and of division and of fractions, would immediately know that the answer must be greater than 1. Because you are trying to see how many 2/3 are there in 1. 2/3 is smaller than 1, so the answer must be greater than 1. So that should come to you immediately. So even if you make a silly mistake here, and if you get an answer less than 1, you should know that you're wrong. That is if you have a conceptual understanding. Now can you think of doing this without using the rule? Or at least, can you give me an explanation why we do this rule? How does it work? Why 1 divided by 2/3 is the same as 1 multiplied by 3/2? So if I just show you how you can graphically think about this. Here's your 1. Say this is your 1. And you're trying to see how many 2/3 there are in 1. So if I draw a 2/3 separately from, here's your 1 again. Here's your 2/3. So you want to see how many of these pieces fit in your one whole. So clearly you can fit in 1, right? There you go. That's 1 2/3. So that's 1. And you can fit in half of a 2/3, isn't it? Half of a 2/3 there in the remaining part. So there are 1.5 2/3 in 1. So that's it. That's the ground level, basic level understanding of how you get 1.5 when you divide 1 by 2/3. This is just applying a rule. I just showed you the conceptual understanding behind that rule. I think I have one more example here. But I think I will not explain that to you. I will leave that for you to think on your own. And notice that I'm taking very simple math as examples here. Work out -3 times -2. And there's nothing to work out. You know the answer immediately. You know it is 6. And again, this comes from applying a rule. What's the rule? Minus into minus is plus. But why? How is minus into minus plus? Have you ever thought about it? You have not, you have just accepted this rule and you're following it now. So this means you have been receiving mathematics as a procedural subject. That makes you lose a lot of beauty in it. So I think I will not try to explain why negative times negative is positive. If we have time later, or if you want me to say it at the end, maybe I would come back and revisit this. I will leave this for you to think about it. Okay, so bring back all your memories about all the math that you have learned and see whether you have a conceptual understanding of these things. Okay, next, the third aspect of math that I think we are going wrong here, and so we fail to see the beauty of math, is this. Math is full of connections, but we learn it as a bunch of isolated pieces. We learn math as disconnected pieces. You don't, you might not have seen the connections between what you have learned. I'll take an example. So I'm going to show you some different pieces of math that you have come across throughout the years of learning math. See what the connection, see whether you can see the connections in the things that I'm showing you. Here's the first thing, this is a Pythagoras theorem from geometry. Here's a different thing that you come across later, the distance formula in coordinate geometry. The distance formula, it's a formula to find the distance between 2 points when you know the coordinates. Here's another one, again in coordinate geometry. By the topics, they imagine it's of a complex number. And finally, here are 3 identities that you learn in trigonometry. So I've drawn from different areas of math here: simple geometry, coordinate geometry, complex numbers, and trigonometry. I hope you have seen. Now, this, I think you may have seen the connection. What is underlying in all concepts is just the Pythagoras theorem. They are not 5 different things. They are the same. They stem from the Pythagoras theorem. So seeing that would make you see math as a connected whole rather than a disconnected thing, something that has no connection with the other. This is just one example. Here's another one. This is what you do. We just did this. This is the strategy you follow when you have to divide by a fraction, when you are performing a division by a fraction. Here's the same thing. You are dividing by a fraction, but the fraction is written in decimal form. Again, you have a strategy here. You multiply both the divisor and the dividend by, by some number, a multiple of 10. So that. And here's when you divide by a surd, by an irrational number, a surd. And then division by a complex number. Now, these are division by different numbers. This is division by a fraction. This also is division by fraction when the fraction is written in decimal form, division by a surd, and division by a complex number. And you have different strategies to be applied in all of these cases. Do you see a connection? This we have a name. We call this rationalizing the denominator. I hope you know that. What you do is, if what you are dividing by is an irrational number, you multiply both the top number and the bottom number by that number itself in order to make it a rational number. So you're transforming Okay. Yeah, so okay, I forgot where I was. Okay, so in this, yeah, we have a name for this third, right? Rationalizing the denominator. What we do is we transform the division by an irrational number into a division by a rational number, because we know how to divide by a rational number. It's the same thing that we do in all these. Now, this will reveal the magic behind the invert and multiply rule in the first case. I'm thinking whether I should leave that to you as well again, or should I explain it to you? And here, when you're dividing by a fraction that is written in decimal form, what you're doing here is the same thing. If you don't know how to divide by a decimal number, so you convert the question into a division by a whole number, because you know how to deal with division by a whole number. That you do by multiplying both the top and the bottom by an appropriate multiple of 10 in order to make the decimal number into a whole number. It's the same thing that you do here when you divide by complex numbers. You don't know how to divide by a complex number, so you change the denominator, the divisor, into a real number by multiplying both the top and bottom by the conjugate. So what we do in all of these cases is the same thing. You are transforming the division that you can't handle. You don't know how to divide by that type of a number, so you turn it into a division by a number that you know how to divide by. So it's like here, it's like this is called rationalizing. This could be realizing, because you're turning the complex number into a pure real number. Here, this could be like wholization. I don't know, you can make up a name for it. What you do here is the same. What you have here is 2/5 divided by 3/4. The bottom fraction, in order to turn it into a whole number, you can multiply both the top and bottom by 4. Okay, I want you to do this and try it and see. What you're trying to do is to turn the bottom fraction into a whole number, and that looks like you are inverting the denominator. I hope you got it. I didn't write it down. So all these are connected, but we don't see these connections when we learn this, that it is the same strategy that goes on in all of these divisions. Here's another one. Remember all the formulas that you have learned to find the area of different shapes. Now, I'm sure you have learned this as separate formulas. You start with the area of a rectangle, which makes sense to you. If something is 3 long and 2 wide, the number of boxes inside is 3 times 2. So that is clear why it is A times B. And then everything else that comes after that, all the formulas for areas that come after that are based on the area of a rectangle. I don't know whether you have seen that. Area of a square is nothing new. It is the same formula as for a rectangle, because a square is a rectangle. And the formula for the area of a parallelogram, by the way, both rectangles and squares are parallelograms. I hope you know that. The parallelogram base times height, that comes from the area of rectangle too, because any parallelogram, if it is slanted like that, because even a rectangle is a parallelogram, if you have a slant one, you can make it into a rectangle. And then it's the same as finding the area of the rectangle who has B as the length and the vertical height as the breadth. Area of a triangle, it's not a separate formula. It comes from area of a rectangle again, because 2 triangles together gives you parallelogram. So parallelogram came from the rectangle. So the area of a triangle comes from the parallelogram. Any triangle is half of a parallelogram. So see the connection. It's not just like you're learning different disconnected formulas, but they are all connected. The trapezoid comes from the area of a parallelogram, which came from the area of a rectangle. So they are all tracing back to the formula of a rectangle. And even the area of a circle, which is pi r squared, is the limit. If you know limits, it's the limit of the sum of rectangles. How you go about deriving the formula for the area of a circle is by trying to think about it in terms of rectangles. Remember, whenever you want to think about the area of something, you try to either reform it into a rectangle or split it into rectangle because the only thing you know is the area of a rectangle. If you can bring that into this, you can come up or derive a formula for this unknown shape. So even pi r squared comes from the area of a rectangle. It's the limit of the sum of rectangles. I'm not sure whether you have seen how it comes. And finally, in integration, what we do, how we find the area below a curve, that we do by splitting this into rectangles. So the area of this is also, it's a limit of the sum of areas of rectangles. So all the area formulas, they're all connected. They all go back to the area of a rectangle. Though you learn them separately, they're all connected. They all connect back to the area of a rectangle. So once you see that, it again, you start seeing it as a whole rather than seeing it as just separate pieces lying everywhere. Okay, then the final aspect of math that I want to share with you that that is an aspect of math, but something has gone wrong for us not to see that, is learning math. I want to say is as enjoyable, but I put can be because not everyone experienced that. Learning math can be as enjoyable as being engaged in some form of an art. It could be like painting, could be music, poetry. Think of any aesthetic thing that you enjoy. Learning math can be as enjoyable as being engaged in art. Where did we go wrong? But we learn math for its usefulness. When we learn math, we want to know, how is this useful? So we learn mathematics for its usefulness only. So until we break out from that, you are missing out on something that is very beautiful in mathematics. Now, when I say this, you might think, of course we learn math because it has applications. Why else would we learn math for, right? Because think about it. This is a question that I'm sure all of us have asked ourselves or asked our teachers at some point in our lives. Where am I going to, when am I going to use this? And it discourages you to learn something if it has no application. I'm talking about math, right? In math, if you feel like this is not going to be useful in my life one day, then why am I learning it? We have to change that way of thinking. Why? Because think about being engaged in something aesthetic, like I said, when you read a book or when you listen to music. Do you ask yourself, when am I going to use this in my life? You don't ask that question, do you? You engage in such activities because that brings you joy, because you enjoy reading a book, because you enjoy playing music or listening to music. You paint because you enjoy painting. There is an aesthetic appeal in it and you enjoy it. You don't care whether it's going to, the activity of engaging in reading a book, or listening to music has a real life application. You don't care about that. Now, math too does have the same quality. It's not the usefulness of math that must draw you into it, but it's wonder, right? You should learn things because it interests you now, not usefulness is a bonus. Now, I will tell you how mathematicians do mathematics. They don't explore math because they think that some commercial application would follow later. That's not why they engage in math. They are just in it for the sheer beauty that they find within mathematics. They are not doing things thinking that this will wind up being connected to the real life and it will help physics, economics, and so on. They are doing it because they enjoy it, right? yeah, to put it very bluntly, they don't do it because because they want to make the world a better place. They don't explore. They don't do. They don't go on exploring mathematics, thinking that, oh, I want to change the world. I want to make it a better place. Although math frequently end up doing just that. But what happens in our classrooms? We showcase mathematics for its practical. Motivate learning math by showing here this has its uses. This is useful. This is going to be useful one day. That's how we sell mathematics, and we shouldn't do that, because just the activity of engaging in math in itself is an enjoyable thing, and that's why you should learn it for, not for the application alone. Two sides. You have to understand both of them. I will show you a couple of quotes from some mathematicians to prove my point. Here's, I think you have heard of Henry Poincaré. He was a French mathematician. He was a theoretical physicist. He says, the mathematician does not study pure mathematics because it is useful. He studies it because it's beautiful. Here's another one. Paul Lockhart is a research mathematician and also a mathematics educationist. He says, the first thing to understand is that mathematics is an art. The difference between math and the other arts, such as music and painting, is that our culture, or I can say our education system, does not recognize it as such. And we never pass this message to students, the learners of math, and we try to sell it for its usefulness. And G.H. Hardy, I'm sure you have heard of him. He's the author of the famous book, A Mathematician's Apology. And he's the mentor of the Indian mathematician Ramanujan. He says, we have concluded that trivial mathematics is on the whole useful, and that the real mathematics on the whole is not. He's someone who did a lot of work in number theory, and a lot of these have no practical even the parts of mathematics that you create, even though you might not be creating it to suit a practical purpose, later you find where it could fit. That's true. But the point is that engaging in math must be for that enjoyment. It must be for pleasure, right? Okay, I think with this, I will revisit. For this last point, my point will be that we must elevate the status of math into an art form and learn how to enjoy just engaging in math. So if I revisit my earlier slide, seeing the beauty of math, as I said, it relies on the way you engage with it. I hope you saw a bit of that. It lies in the way you perceive what math is. And it lies in the way you understand it, the way you make sense of it. So with the 4 aspects that I was trying to share with you, I hope in the future, you will interact with or engage with math a little differently. You will perceive it a little differently, and you will try to make sense of it in a conceptual way so that you see what you failed to see before. Thank you. I may have taken more than I should.
No, it's okay. Thank you very much, Dr. Gaya. It's a very interesting and nice presentation. And if you would like to ask any questions, please free to ask.
Yes, dear students, I hope these are many of you are students. If you have anything to ask, please do. Vishwa is asking for the recording. I think he's messaging me privately. Is it so? Yeah. Vishwa, I think you can put that message to the host, Professor Shanta sir. Then he will let you know how to get the recording.
So we have actually a web page in IPSL.
Right.
Then we will distribute to that web page.
Right.
And I have a question about the actually not about question, but so we are mainly most of the students are facing some competitive examinations. So it's possible to use the method that you explain in that type of situations. I mean, not only for the normal things, for advanced mathematical techniques.
Can you repeat the last part, Shanti sir? I didn't get the last part.
Actually, when sometimes
we face
our students have to face
competitive exams.
Examination, that competitive examination, for example, advanced level examination in mathematics and O-level exam. So it's possible to use this type of techniques in those type of competitive examination.
That's a very good question, sir, because this is something that I get often when I try to share this similar type of thing with teachers. And before they ask, actually, I tell them, before you ask, because I know that what you will say is that we have to do this much of work and this is the time that we have. How are we going to implement all this in our classrooms? My answer to that is, it might look like a lot that, so when you say, go to these conceptual levels of teaching, show them why things work, how things work, all that. Initially, for certain things, initially it might take a longer time than when you teach something in a procedural way. But in the long run, what happens when you teach procedurally is, anyway, you're going to spend a lot of time because they don't understand, they find it hard as they go on. In the long run, you're going to face difficulties because you are teaching procedurally. But when you teach conceptually, even though it might take a little more time in the beginning, the later on it becomes easier. You get the attention of the student, they start liking the subject, and since you're building one on top of the other, you're seeing the concepts, it all starts to make sense. In the long run, it's going to be easy. And another thing is that why people resist towards this is because even they themselves are not familiar with it. We have learned, as teachers, we have learned procedurally, so we are reluctant to go into that unknown realm. We think that it's going to be difficult for us. But I've tried it myself, and I've seen its fruits. So I think it can be done. I have some messages sent to me privately. One is Yesit is asking, are there any courses we can follow mathematics? I'm not sure, Yesit, what you mean by that. Maybe you can clarify on that. Hansarandi asking, could you please recommend books to enhance knowledge in mathematics? Again, there are so many books. If you like, especially to increase your interest in math and to be able to see the beauty of math, Hasarandi, I can not books. I can refer you to some papers, beautiful articles written about mathematics. That would awaken that part in you that would make you love mathematics. Yesit is saying diploma courses. I mean, like diploma courses. Are there any courses to follow in mathematics? Still, I'm not sure what you Shantasa, you can't see these questions. No, somebody's asking whether there are any courses they can mathematics. So we can't hear you.
You go to
Chancellor, you are
open-
muted.
Yeah, if you are going to Open University, they are conducting some diploma level and even degree level courses. But other than that, I don't think we have courses like that. And I have another question. If you don't have
Yes, sir.
any more questions. So how about the development of mathematics or physics education in Sri Lanka? Do we need to develop that field? And how about the knowledge of teachers about this type of methods and especially teaching mathematics with these simple methods? Do we need to develop
Yeah.
this field, or how about your idea about mathematics
So
education or physics
in my
education?
view, yes, sir, in my view, we definitely have to develop the education aspect of all these subjects. We do have physics education now that has been started in the Columbia University. There is mathematics education that has been started in the Columbia University and Peradeniya University. Science education, all these, they have, these things have to university, we have to initiate and take this forward. And what I see is that when we take this to teachers, they are really keen to know these things. It's just that they don't have the resources. There are no programs, enough programs for them to get engaged and to take part. So actually, if that is why we started this thing called Meta Hub, to bring all the teachers and to provide them with the resources that are available in math education Sri Lanka, to bring them that knowledge. So there is definitely a requirement, a need to develop mathematics education as well as physics education in Sri Lanka, and that will do a lot of good to our teachers.
Thank you. Any more questions? I think if there are no more questions, I would like to thank today's speaker, Dr. Gaya Jayakody, for accepting our invitation and giving an excellent presentation about mathematics and the way of understanding mathematics, those things. And also we were able to lot of things using this topic. So I would like to invite Dr. Rahubad, Joint Secretary of IPSL, for giving vote of thanks. Dr. Rahubad, over to you.
Thank you, sir. Dr. Gaya Jayakody has successfully conducted the lecture in Beauty of Mathematics. In fact, that was a very supportive moment and helpful moment in regarding enhancing our knowledge in mathematics. On behalf of the President, Professor Shantha, and Council members and all the members, I would like to convey my sincere gratitude to Dr. Jayakody. Dr. Jayakody, I wish you all the very best. Thank you, organizing committee who work to make this event success. Thank you, audience, for your participation, and good evening, and have a nice weekend.
Thank you. Thank you, IPSL, for having me. Thank you.
Thank you very much.